Dear conference participants, my name is Yaroslava Emelianenko. I am PhD student at the Institute of Software Systems of the National Academy of Science of Ukraine. Here I present my work on the design of cluster computing architecture to improve training speed of the Neuroevolution algorithm. Genetic algorithms are a promising field of machine learning, particularly suitable for tasks related to optimization and control, reinforcement learning, artificial life simulation, coevolution of swarm agents, and so on. One of the most popular and powerful among them is the Neuroevolution of augmenting topologies. The algorithm and its extensions allow us to apply creative forces of natural evolution to design compact and energy-efficient topologies of the artificial neural networks. Controllers based on such artificial neural networks can then be used for inference in environments with very limited resources, such as robots, unnamed aerial vehicles, networking edge devices, IoT devices, etc. In this presentation, I will briefly describe the fundamentals of the NEAT algorithm. After that, the proposed architecture design of cluster computing using the Ray framework will be presented. Now we consider the NEAT algorithm fundamentals. The most important feature of the NEAT algorithm that defines its potential is an ability to evolve the topology of artificial neural networks during the learning process. The importance of gradual augmentation of network topology became obvious if we consider how it is implemented by NEAT. When exploring search space of solution, the NEAT algorithm starts with the simplest basic network topology that comprises only input and output nodes of the solver ANN. After that, with each epoch of evolution, the topology of solvers become more complex, and the most complex multidimensional topologies are related only at the final stages of evolutionary process. Furthermore, the most suitable topological structures found during evolution are preserved by NEAT algorithms through generations due to its inherent features. Such approach of gradual complexification of solvers' topology considerably reduces the solution search space during the training. While solution search space is a huge drawback of other evolutionary algorithms, which effectively address it by NEAT due to its key feature of design, which we consider next. Now we are going to consider the key features of the NEAT algorithm. First, topology augmentation through gradual complexification. Learning process starts with basic simple topology and gradually increases its complexity based on results of analysis of solution search space. At the same time, NEAT has ability to preserve minimal found topology that is able to generate ultimate solution. As a result, produced topology of artificial neural network usually become compact and energy efficient. Second, speciation. It separates population into evolutionary niches using genetic distance between organisms, which is based on similarity of genomes. Its main goal is to reduce negative adaptation pressure caused by increased complexity of novel organisms when new node or connection added to the genome of the offspring. Third, mutation. It plays an important role in keeping genetic diversity of the population during evolution and prevents objective function from stalling at local minima when the chromosomes of organisms in the population become too similar. Mutation operator changes one or more genes in chromosomes according to the mutation probability defined by experimenter. Fourth, the innovation numbers. It is the most prominent feature of the NEAT algorithm that allows to solve issues with overlapping parts of genomes of ANN solvers. The overlapping genome parts produce similar ANN topologies that estimate the same function, but were embedded in different genome structures during reproductive crossover. With innovation numbers, we can easily differentiate them without complex topological analysis. Crossover, or recombination of genomes, allow for two or more champion organisms within specific population niche to mate and produce offspring that inherit important characteristics of both parents. It is during this process that the mentioned above innovation numbers allow us to identify overlapping excess or disjoint genes. Despite its prominent features, there are several drawbacks that related to the NEAT algorithms. Genome of each organism in the population directly encodes a certain topology of the ANN solver. As a result, the population size and the size of encoded ANN are limiting factors. With a large population, we need to have more computing resources to evaluate the evolutionary process. Thus, we can only work effectively with relatively small ANN topologies and moderate populations. Second drawback is chosen objective function applied to calculate the fitness of organisms in a population works well for simple tasks, but often collapses into local minima traps for more complex tasks. Another drawback is slow training associated with a large number of calculations at the stage of fitness evaluation of each organism in the population. The first two drawbacks can be addressed using extensions of the original NEAT algorithm, and the later one is a subject of interest in this presentation. Now we consider how Ray framework can be used for distributed training of the NEAT algorithm. Ray is a general-purpose distributed cluster computing framework developed within University of California, Berkeley to address the ever-growing need for distributed parallel computing for reinforcement learning tasks. The main goal of the Ray framework was to develop a framework capable of processing heterogeneous tasks in a massively distributed manner, to handle over 1 million scheduled tasks per second with milliseconds level latencies. Heterogeneity of tasks considered both in the terms of execution time, for example, a task hand takes milliseconds or hours, and resource usage. For example, tasks can be executed by GPUs, CPUs, or TPUs. TPU is Tensor Processing Unit. Our proposal is to use the Ray framework to handle the most time-consuming task in the Neuroevolution algorithm, the simulation of the objective function execution to estimate the fitness of each organism in the population at each epoch of evolution. We propose the following architecture to support distributed training using Ray framework, which consists of NEAT executor. It's the main process executing evolutionary training using our Golang library implementation of the NEAT algorithm. Ray task scheduler. It's a Ray driver application scheduling remote tasks execution and exposing remote procedure call API interface to the NEAT executor. And a collection of distributed workers. It's a cluster with Ray stateless workers to perform fitness estimation simulation for each organism in the population. You can see our proposed architecture on the picture at the right of the slide. Now I'm going to describe proposed solution in more details. The NEAT algorithm implements a direct genome encoding scheme which allows generating a solver ANN directly from an organism genome. At the same time, the implemented genome encoding scheme has a very compact textual representation that can be easily encapsulated in standard post-HTTP requests. Using this coding scheme, we can easily encode the genomes of a single organism or all organisms in a population together. As a result, at the end of each evolutionary epoch, we can send the encoded genomes of all organisms in the population for evaluation by distributed array workers in just one network call. This will greatly reduce the latency of this operation. After receiving the encoded genomes of all organisms in the population, the array task scheduler reads the encoding of each individual genome and schedules tasks for remote fitness evaluation by stateless cluster workers. Eventually, each remote worker in the array cluster receives the encoded genome of the organism as input, decodes it into an NNN solver, and applies it to solve the simulated objective function. The estimated fitness of the organism and the flag indicating whether the objective function has been solved are then returned back to the array task scheduler. Ultimately, the array task scheduler collects data from all remote workers and returns it to the NEAT executor in a one batch. Using the obtained fitness values of each organism in the population, the NEAT executor creates a new population of organisms for the next epoch of evolution, or terminates evolution if a solution has already been found. For a detailed description of the proposed algorithms, please refer to my conference paper. Now we can make the following conclusions. Despite all the powerful features inherent in evolutionary algorithms, they are still not widely used due to their slow training speed. I will demonstrate how this obstacle can be mitigated by using a state-of-the-art cluster computing framework that allows the most time-consuming steps of evolutionary learning to be transferred to an almost limitless cloud infrastructure. Using the proposed design, it is possible to develop industrial microservice systems with trained NEAT models without any additional model tuning. This can significantly reduce the maintenance time of the ML operation cycle. In addition, this approach allows implementing self-supervised learning systems that continuously train deployed models. The source code of the implementation of the NEAT library using the Go programming language is available in the GitHub repository. The link to the GitHub repository you can see just beneath. Thank you for your attention and have a wonderful conference day.